Assalamualaikum and a very good morning to our lecturer, Dr. Nur Hazwani. This is a proposal video for our Chem-E car project. We name our car as reactor racer, that's synonym to the car moving when there's a chemical reaction occur inside it. So my team consists of 5 members, including me, Yasin, Eva, Shahira, Fadila and Broderick. In this video, we are going to present to you everything that we planned for our project. But before that, we would like to introduce to you our first car design for this project. As you can see, this is the view from the side and the other one is the view from the top. This is our planning throughout the semester for this Chem-E car project. So, let's jump right into the introduction.
First of all is the introduction to our Chem-E car. A voltaic cell is a device that produces electricity from a chemical reaction. It works by using 2 different metals called electrodes that are placed in a solution that allows ions to move. One metal gives up electrons, which is called the anode, while the other receives them, which is called the cathode. The flow of electrons between the 2 metals through a wire creates an electric current. Voltaic cells are used in batteries to power many everyday devices. Now, I would like to pass the presentation on to Eva.
There are 3 objectives for this experiment. First is to create a battery that can power up a car. Second is to check whether the stopping mechanism is suitable or not. And the last one is to design a car that can carry a fixed amount of loads. The materials for this experiment including zinc strip, copper strip, sodium chloride or sulfuric acid solution, conductive wires, distilled water, mortar, alligator clips, and 250 ml beaker.
For methodology, measure 100 ml of distilled water using a measuring cylinder and pour it into the beaker. With 5 grams of sodium chloride using electronic balance. Add the sodium chloride to the beaker and stir with a glass rod until fully dissolved. Next, place the zinc strip and copper strip into the beaker. Attach an alligator clip to the exposed part of the zinc strip, which is anode, and copper strip, which is cathode. Connect the wire from the zinc strip to the negative terminal of the motor and copper strip to the positive terminal. Lastly, record the voltage output.
Next is stopping mechanism. We apply electrolyte depletion as the mechanism to stop the battery work. So the theory is, as the reaction occurs, the concentration of zinc ions increases in the solution and copper ions are gradually removed. Over time, the electrolyte becomes less effective in facilitating the movement of ions between the 2 electrodes. As the ions are depleted, the battery's ability to conduct electricity decreases. This will continuously lead to a gradual drop in voltage and current output, and the battery will stop working. In this experiment, the zinc strip and copper strip will fully dissolve and then the car will stop moving.
Expected result. For the value of voltage, we could get 3.0 until 3.3 volt, and for the current value is 0.5 until 2.0 milliampere. The result of chemical reaction for the oxidation, zinc oxidized to the ion zinc 2 plus 2 electron. For reduction process, ion copper 2 plus with 2 electron will reduce to copper atom. So, for the overall equation, zinc plus with ion copper 2 plus will give the result of ion zinc 2 plus copper.
Next, we will be discussing the cost estimates for our project broken down by each required component. The costs are presented in ranges to reflect possible variations depending on the supplier or quality of materials chosen. The cost of wires, which will connect the components, falls between 4 ringgit 50 cent and 9 ringgit, depending on the length and type of wire we select. Next, for alligator clips, which are crucial for creating temporary reliable connections, the cost ranges more widely from 9 ringgit to 22 ringgit 50 cents due to differences in sizes and quality. Next, the motor, a vital component to drive the project mechanism, also shares this wide range of 9 ringgit to 22 ringgit 50 cent depending on its power and specifications. Boxes, which will house the components and provide structural support, range in cost from 4 ringgit 50 cent to 13 ringgit 50 cent, influenced by the material and sizes. Lastly, we have plastic bottles, which serve as part of the project's structural framework. These have a relatively low cost ranging from 1 ringgit to 2 ringgit. Now, based on these individual component costs, we have calculated two potential estimates. First, the low estimates of the total project cost if we source materials at the lower end of the price range is 28 ringgit. On the other hand, the high estimates, assuming we for higher quality of more expensive components, comes to 69 ringgit 50 cents. This breakdown allows us to adjust our choices based on our budget and the required quality for the final project.